is batteries. Batteries for UPS systems. The other name we have for that is stationary batteries. In other words, they don't move, they're not attached to a forklift or anything like that. So they are stationary batteries. Without further ado, we're using Teams now for our webinar, so I don't have to check if everybody can hear me, because you should be able to hear me. But we'll just go through our usual checklist of things. First of all, I'll introduce myself. My name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls. I have more than 23 years in the industrial UPS industry, so pretty much I've been there, done that, seen everything there is to see. And I've worked with all of the major UPS and charger manufacturers. I know pretty much everything that's out there. I'm learning every day still. I don't pretend to think I know everything, but I do know quite a bit. The webinar will be recorded. That's a very popular question. It will be recorded, and it will be uploaded to our YouTube account within the next 24 hours. So all of our webinars are available at that website. And if you go to the chat, you'll be able to see that our wonderful marketing team have put all the links and everything that you need to get to that YouTube site. So it will be recorded, and it will be there within the next 24 hours. And the webinar, depending on how much I rabble on, usually lasts about 1 hour. So that is our plan for today. So let me just open my chat bar. Oh yeah, one more thing. If you have any questions throughout the webinar, please click at the top of your screen in the Q&A, not in the chat. If you put a question in the Q&A, then that way I can, at the end of the webinar, I can go to the Q&A and find out any questions that we've had, and hopefully be able to answer those questions as best as I can. And I like your comment, Christopher. Yes, my trust in Microsoft might be misplaced. It worked last month, so hopefully it's going to work again this month. Okay. So let us move on. So our objectives today are to understand battery terminology, understand the basics of the main types of industrial battery understand the purpose of a battery in a backup power system, and to discuss the pros and cons of different batteries. It's slightly different from what we advertised it to be. We were going to do some battery sizing stuff, but we had a lot of emails asking us to go into the pros and cons of different types of batteries. So that is what I'm going to focus on at the end today. So hopefully you understand why I've done that. So first of all, we're going to go over all of the terminology that we're going to use throughout this webinar. And I know most of you will know this, but we have to go over the basics so you know what we're actually talking about. So first of all, we're going to discuss voltage. Now, there are lots of different voltages involved when it comes to batteries. And first of all, the first thing you'll hear is nominal battery voltage. And that's the industry convention. Battery manufacturers use this as a simple nominal value for design and classification. Okay. For example, a lead acid battery, the nominal cell voltage is 2 volts. A nice, easy number that everybody can get their head around. Okay, so that's what nominal voltage is, and we'll go into these in a little bit more depth as we go along. Then we have the float voltage, and that's the standard charger voltage required for the battery to maintain adequate charge. So that's to overcome the losses that happen in normal operation of a battery. So it's the exact charge voltage needed to keep the battery at an adequate charge and not overcharge it and not undercharge it. So that's what float means. Equalize is an increased voltage specifically used for vented lead acid cells and sometimes NiCad cells that may cure unbalanced cell voltages that arise in a series string. So it's quite kind of a specialized voltage that you may need to use if you have unbalanced cells in a string. Commissioning charge, that's an increased voltage usually listed for NiCad cells. And it's a specialized initial long duration charge applied to new or batteries that have been stored for a very long time before they are put into operational service. And its purpose is to ensure that all the cells are completely and utterly fully charged, balanced in voltage, and ready to deliver at their rated capacity. So that's what commissioning charge means. And then the last voltage that we're going to discuss is the end of discharge voltage. And that's a voltage specified by a battery manufacturer when a battery is considered to be empty. So typically for lithium ion, it's 3 volts. For lead acid, it's 1.75 volts. And for NiCad, it's 1 volt. But these do vary slightly depending on what you're trying to get out of the battery. So that's all of the voltages that we may mention throughout this presentation. The next terminology we're going to go over is current and duration. And the most popular one that we hear all the time is ampere hours. Okay, AH is the designation for it. And that represents a battery's total energy storage capacity in amps, and it indicates how much current it can provide over a specific time, down, and you have to remember this, to a specific voltage, and it's quoted at a specified C rating. Now, I know that's very wordy, and we'll get into it in a little bit more in detail what ampere hours actually is. And it's usually for longer duration batteries, for anything up to really 30 minutes up to 20 hours, okay? For short duration batteries, they tend to go for watts per cell. And that represents a battery's total energy storage capacity in watts. And it indicates how much current in watts, basically power, it can provide per cell for a specified time down to a specified voltage level. And usually watts per cell is for batteries durations that are listed in minutes. And they're usually connected to UPS systems, and it's usually UPS systems in high-powered data centers that use watts per cell. Short circuit current, that's how much current the battery can deliver if a short was placed across the main positive and negative. So if you got a big steel wrench and you drop that across the main positive and negative of the battery, that's how much short circuit current the battery can deliver. And it's usually a large amount. You'd be surprised how much current a battery can supply. Then we have maximum discharge current, and that's the highest ampere rate at which a battery can safely release its stored energy without causing overheating, damage, or reduced lifespan. And then the last one we're going to discuss is current limit, and that's the battery manufacturer's recommended maximum charge current allowable from the charger to return the stored energy into the battery without causing any overheating, damage, or reduced lifespan as well. Okay. And then what I'm going to do here is go over some parallel series configurations. Okay. So what we have here at the top left is two 12-volt batteries connected in parallel. But let's go back one step. Let's say we just have one 12-volt battery. Okay. And then we have the positive and the negative connected. And let's say this is a 100 ampere hour battery, okay? To make things nice and easy, we'll use nice round numbers so we don't overcomplicate things. So if we had a 12-volt battery that was a 100 ampere hour battery, then in theory, what we would have is we could say that this battery could supply its load circuits at a 12-volt nominal voltage, 100 ampere hours. Okay, so let's say that was at the 10-hour rate. That means it could give 10 amps for 10 hours. That equals 100 ampere hours. Okay, but let's say now that we connected two of these identical batteries in parallel. So we now have a 100 ampere hour battery here, and we have a 100 ampere hour battery here. Now, hopefully you should know if you connect two voltages in parallel, the voltage does not change. So we still have a 12-volt battery. So at this main positive and negative here, you would get 12 volts. But now what you have, because you have connected two batteries in parallel, you now have a 200 ampere hour battery. So once again, if we said the load was going to take 10 amps, so instead of getting 10 amps for 10 hours, now in theory we would get 10 amps for 20 hours. We have increased the capacity of the battery by adding another battery in parallel. Okay, now please remember, some people who are more expert in batteries may be shouting at the screen, well, you have to know the duration of the ampere hour and the C rating and all that kind of stuff. I will get to that eventually, but this is just really the basics of series and parallel batteries. So that's the most simple configuration. When you put two 12-volt batteries in parallel, the voltage does not change, but the capacity does. Okay. But now, on this one here, they have put two 6-volt batteries in series. Once again, let's say this is 100 ampere hours, and this is 100 ampere hours. Okay, now these are 6-volt batteries. When you put batteries in series, the voltage does increase. So now if you connected a voltmeter across a positive and negative, you will get 12 volts. But the capacity when you have them in series does not go up. So you will have 12 volts at 100 ampere hours. It's not at 200 ampere hours, it's at 100 ampere hours because they're in series. Okay, so we have now created a battery using two 6-volt monoblocks in this circumstance that will give us an overall voltage of 12 volts. And because each battery can supply 100 ampere hours, the total ampere hours for this 12-volt power going out will be 100 ampere hours. So when you put batteries in series, the capacity does not go up. It is only the voltage that goes up. Okay. And then on the right-hand side here, this is more common, what you will see in industrial facilities. You will see individual cells connected together. So in this circumstance here, we have 2-volt cells, okay? And they've connected 6 of these in series. Once again, if every single battery here is 100 ampere hours, okay, at 2 volts, that means the overall string voltage, if we measured it with a voltmeter, is going to be 12 volts. 1, 2, 3, 4, 5, 6 cells times 2 volts will give us 12 volts. So the voltage does go up. But remember what I said, when you connect batteries in series, the capacity does not go up. So you will get 12 volts at 100 amps. So this battery here would give you, if I go back to this previous example here, and we were taking 10 amps out, it would still give you 10 amps for 10 hours, roughly, okay, at 12 volts. And one more thing, if you connected 2 of these strings in parallel, and remember, if these were 100 amps, we are still going to measure 12 volts, because we've now connected 2 sets of cells in parallel. But now we have parallel strings, 100 ampere hour and 100 ampere hour. So you would get 12 volts at 200 ampere hours if you connected these in parallel. So hopefully I haven't confused you too much, but that's all the different parallel series configurations that you will see. And depending on what you need at your plant, you may need to go with parallel strings for power. You may need to go to parallel strings because you want some redundancy. It's all down to the design engineer at the end of the day to figure out exactly the way that they want to connect their batteries. Okay. But remember I said I would come back to ampere hours? Remember, ampere hours are for a specified duration. So here's a data sheet from ENESYS, and this is for the EC series of batteries. Okay. Now, the first box here says the nominal ampere hour capacity. Okay, so for the EC5, they say that that is a 200 ampere hour battery. But that's not the end of the conversation. They say, okay, 200 ampere hours at what duration? And I know that ENESYS always usually quote at the 8-hour rate. So if you look at this table here, this column here, at the 8-hour rate, it's saying you will get 25 amps. And if you multiply 25 times 8, this value here, that equals 200 amps. So that is why they are saying that the EC5 gets 200 amps, which is 25 amps at the 8-hour rate. But please, please, please remember the discharge graph for a battery, especially lead acid batteries, is not linear. Okay. And that 200 ampere hours changes over the time period. And more importantly, it's easy to see here. And you can see this box that I've highlighted here. At the 1-hour rate, most people would say, well, if it's a 200 ampere hour battery, at the 1-hour rate, I should get 200 amps. That would make 200 amps per hour. But because the graph is not linear and the discharge at higher rate currents is not as efficient, then the capacity is reduced to 100 amps per hour at the 1-hour rate. And in truth, if you go past the 8-hour rate and you go to the 24-hour rate, if you multiply 10.2 amps by 24, the capacity will go up. That actually adds up to, I think it's 248 amps, ampere hours. Okay, so you do have to pay attention to the specifications from the battery manufacturer, and when it says what the nominal ampere hour capacity is, you have to know what C rating that is. And for this cell here, the C rating is 8 hours. So what it should say is for the EC5 it's a 200 ampere hour battery at the C8 rating. In other words, you will get 25 amps per hour for 8 hours. Hopefully that explains that. So now we'll go over individual cells and the types of cells that are out there. So for a lead acid cell, and this is true for all lead acid cells, the positive is an anode lead dioxide, which is a PbO2. And believe me, I don't get into the chemical of things. I'm not good at chemistry whatsoever. And the negative post, or the cathode, is lead. Okay, so positive is lead dioxide and the negative is lead. Okay. And then we have the electrolyte is H2SO4, which is sulfuric acid. Okay. And if you put a lead dioxide plate in this tub, and you put a lead plate in this tub, fill the tub with sulfuric acid, and you put a multimeter across the positive and the negative post, the nominal voltage of the lead acid cell would be 2 volts. Now, we'll go into why that's not exactly accurate in a little bit, but in the grand scheme of things, to make things easy, that's what the industry standard says. So that is for a lead acid cell. So all lead acid cells basically come to a nominal voltage of 2 volts due to the plate structure, what they're made of, and the electrolyte. Okay? It doesn't change. 2 volts for each cell. So the question is, what is this that's on the screen? Is it a cell? Is it a battery? Is it a string? Is it in a monoblock? And the answer is, this is classed as a monoblock, okay, or a jar. and it contains 3 cells. And you can see that they're separated with these partitions here. Okay, there are 3 cells in this monoblock or jar. Okay, so each cell, remember, for a lead acid battery is 2 volts nominal. Okay, so this system has to be connected in a specific way. So that has to be connected, that negative has to be connected to the positive of the next one, and this negative would have to be connected to the positive of this one here. Okay, and then you would have your main cable coming in here and your main cable coming out here. And if that's the main positive and that's the main negative, and this would be a 6-volt monoblock that has 3 cells inside it. Okay. And that's what it looks like. A jar with 3 cells connected in series. It would give you 6 volts nominal when they're connected together the way that they should be. And most of the lead acid manufacturers, when they list their model number, for Enesis, this is a 3cc5. The 5 tells us that there's actually 5 plates in here. So we've got 1 plate here, that's a negative plate. Another plate here is the positive plate. There's another negative plate in there. So that's 3, positive plate here, and a negative plate here. So that's 1, 2, 3, 4, 5. So there are 5 plates per cell in this model of battery. Okay, so that's why they call it a 3cc5. And I've zoomed in there so you can see them. There is always more negative plates in a lead acid battery than there are positive plates, because you have a negative plate on the left-hand side and a negative plate on the right-hand side and it helps with surface area and providing the power that's required. And then to add capacity, all you need to do is add more plates. So you can see here now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So this is probably a 25 plate battery. Okay, now remember that this is still a 2-volt cell. It's actually a 2-volt monoblock or a 2-volt jar. So this will only give you 2 volts, but adding all of these plates together gives you more surface area, which gives you more capacity. And that's how batteries work. The more surface area of the active plates that you have, the more capacity that you're going to get. And that's why batteries that have more capacity are just larger, because you need the surface area of the plates to transfer that power out to your load circuits. And that's all the battery manufacturers do. To get more ampere hours, they just add more plates. Okay. And then the next question is, what's this? Well, this is what we actually would call a battery string now. Okay, so we have cells. We've talked about jars or monoblocks. When you connect multiple jars or monoblocks in series, then that becomes a battery string. Okay, or most people will just call it that's their station battery, or that's their UPS battery. That's the overall battery of everything connected together. Okay. And for lead acids, there's many different variations. On the left-hand side, what we call our vented lead acids, and that is when you can see inside the cell. Some other people call them wet cells. It's when you can see the electrolyte inside, and there are usually flame arresters here. We've got vent caps here for shipping, but if they have flame arresters here, they actually do vent hydrogen into the atmosphere when they're being charged. Okay. But on the right-hand side, we have what are called valve-regulated lead acid batteries. They used to call them sealed batteries, but they're not sealed because they do have small valves. Every single one of these has a small valve that does release some pressure, some hydrogen out into the air. But what they try and do is recombine the hydrogen that's emitted back into the cell, so there is no loss in the electrolyte. Okay, so that's why they were called sealed originally. So they're not actually sealed, but they do try in normal operation to keep as much of the electrolyte inside the jar as possible. Okay, and in truth, for a valve regulated battery, especially for stationary batteries, these are going to be AGM, which is absorbed glass mat, or they're going to be gel batteries. So the electrolyte inside these batteries here is not actually free and you know, like they would say, sloshing around inside the battery like the one on the left-hand side. It's either in a gel or it's absorbed into a glass mat. Okay. And as you can see, for this 12-volt monoblock, for this lead acid battery, this is a VRLA, valve regulated lead acid. You can see the valves very clearly here. And you can see we have 1, 2, 3, 4, 5, 6 cells. 6 cells in series together make a 12-volt nominal battery. Okay. And then I'll just go over quickly the other technologies. For a NiCad cell, the positive plate is nickel hydroxide. The negative plate is cadmium hydroxide, and the electrolyte is usually potassium hydroxide. But it's the same principle as a lead acid battery. You have one plate with nickel hydroxide, one plate with cadmium hydroxide, and then the electrolyte is potassium hydroxide, and that then generates a voltage between the two plates electrochemically. Okay. And you can see here that this are the different types of batteries that this manufacturer, Saft, offers. This one here has 4 cells. In fact, most of these ones have 4 cells. So these are 4-cell monoblocks. Actually, this one here has 6 cells. This large one here has 6 cells. And this one here, actually, this is one monoblock, and it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cells in it. But it's still one monoblock. Hopefully I'm not confusing you with all this terminology. And then this is a battery string where they connect. You can see here there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 monoblocks connected in series, and that makes a battery string. Okay. So a lithium cell, slightly more complicated. I am not, I'll be quite honest, I'm not really a technical expert on lithium cells, but you can see the positive electrode is aluminum foil, and then it's surrounded by phosphate, iron, and lithium. So this would be a LiFePO battery. It's a lithium phosphate iron battery. And then the negative plate is carbon graphite, and the electrolyte is lithium salt. Okay, so, and then we have a separator down to separate the two positive plates and the negative plates, or electrodes, should I say. Okay, so that is now obviously this is for a LiFePO cell, a LiFePO4 cell in particular. There are many different types of alloys and metals that are used in different lithium configurations to give you different characterizations of the lithium cell, more power per for size, etc. So it's always going to change, but this is a general overview of a LiFePO battery. And this is what it looks like. Okay, this is a Saft VL lithium ion cell. Okay, so this is a lithium ion cell. And what they do is they put this inside of a module, usually, that looks like this. What is this? It is a module. And this is still sticking with the Saft brand, and for no particular reason except for we had access because we partnered with Saft in some projects. So we have pictures and documentation from them. This isn't a testament to Saft or any other manufacturer. So inside here, you will see that there are numerous cells that look like this connected in series and parallel to give the rating that they need. So this is called a module, and here is the main positive, and this is the main negative, okay? And then what they do is they put the modules in series to get the correct battery string that they need inside a cabinet. So this is classed as a lithium battery string. Okay, so we had the lithium cell, then we had the lithium module, and now we have a lithium battery string. Okay. And then the flavor of the month is the sodium metal chloride cell, or the salt battery. Okay. So the positive plate is here, and the negative plate is here. And you can see that the negative is molten sodium, and the positive is a nickel chloride substance. And then we have a beta alumina separator to separate the two, the positive and the negative. And then basically that's how the sodium metal chloride cell works. I didn't want to say sodium tetrachloroaluminate. I thought it was going to mess it up, but that actually that's what the positive is. It's a mixture of nickel chloride and sodium tetrachloroaluminate. The important thing to know about salt batteries is this one here. It says molten salt. And to get molten salt, you have to heat it up to around about 300 degrees Celsius, which is extremely hot. So these batteries only operate when they're heated up to a certain temperature to basically melt the salt inside. Okay. So that is a sodium metal chloride cell. Okay. And that is what the cell looks like. So this cuboid here, I would say that's what it is a cell, and they connect them in series and parallel inside this module, okay, to get the capacity and the voltage that they require, okay. And you can see, if you look here, this is actually insulation material. It's foam, high density foam to insulate it. So there is a heater inside this salt battery module that heats up these cells to melt the salt. And then there is really thick insulation to keep that heat in as much as possible for efficiency purposes. So, there's a large portion of the module size is taken up by that insulation. And then that's what the module actually looks like when it's not cut into. This is the most popular salt battery in the United States at present. It's manufactured by Horion, who used to be FZ Sonic. Okay. And then you can put those modules inside a cabinet like this and then connect them in series, and that gives you your battery string. Okay. And if we go back to the start, voltages. Cells are always listed at nominal voltage. Okay, so for a lead acid, it's 2 volts per cell. For a NiCad, it's 1 volt per cell. For lithium, it's approximately 3 volts per cell, but you must check the datasheet based on the type. Okay, because there are many different technologies that have different nominal voltages. And then for the salt batteries, they're usually 2.58 volts per cell at 300 degrees Celsius, but are usually listed at module nominal voltage. So I put a table underneath here. So this is the most popular one that we're seeing in the UPS and industrial facilities. It's a 125 UP80, and it's saying that the nominal voltage of that battery is 125 volts DC. So that is how the salt battery manufacturers are listing their nominal voltage. It's not by cell, it's by module voltage. Okay. So in the industrial UPS and switchgear world, the majority of batteries contain 60 cells of lead acid. Okay. And that's a nominal string voltage of 120 volts DC. Now, this is somewhat changing. There are some systems that operate at 240 volts DC, which would be 120 cells of lead acid. But historically, for switchgear systems and for industrial UPS systems, the nominal string voltage used to be 120 volts DC. That was a standard that was adhered to quite stringently historically, but it is changing now. For NiCads, that means you would usually use about 96 cells for a nominal voltage of 115.2. For lithium ion and sodium metal chloride, which are usually modular, the manufacturer designs these models to match those industrial needs. So basically, the lithium ion and sodium metal chloride or salt battery manufacturers, they know that we're going to use those batteries in an industrial environment. So they match their modules to match this lead acid 120 volts on NiCad for 115. So they match their modules to make sure it's roughly in that ballpark. And the only thing that drives these voltage selections is the tolerance of the loads that they supply, which we'll go into in just a moment. And obviously there are other voltages used. 24 volts is used quite a lot offshore for fire and gas systems and ESD systems. 48 volts is telecoms. And we are seeing more UPS manufacturers out there who are now using 240 volt DC bus or a 480 volt DC bus, because the higher the voltage, the lower the current, and therefore they can save on wiring, semiconductors. Everything's cheaper when you work at a higher voltage because it uses less current. They're inversely proportional when it comes to power. So for a 120 volt nominal lead acid system, sticking with voltages, which is 60 cells, the float voltage, which we mentioned at the start of the presentation, should be about 135 volts DC, but you do need to check the battery data sheet to make sure what that should be. The equalized voltage will be about 139.8 volts, which is 60 times 2.33 volts. And remember, that's for vented cells. Most valve regulated lead acid batteries manufacturers, they recommend that you don't equalize those batteries if at all possible. And it will tell you in the data sheet for that battery. The end of discharge voltage for a lead acid battery is usually stipulated at 105 volts DC. And that is a standard that's been chosen by engineers over time. And that is 60 cells times an end voltage of 1.75 volts per cell. In truth, you can discharge a lead acid battery down to 1.6 volts per cell if you really, really wanted to. But the battery manufacturers say that if you go past 1.6 volts per cell, you may be causing irreversible damage to the lead acid battery. So that's why this safe margin of error was given, and we discharge batteries down to 1.75 volts per cell, which is a total of 105 volts for a 60 cell system. So therefore, we can say that the DC voltage range that the load should be able to work at is 105 volts on the low end, 105 volts, to 140 volts on the high end, which is just above this equalized voltage. So our DC loads, whatever is connected to this battery, must be able to operate between those two parameters. Okay. And we say, and people say, well, why is that? Well, because the battery manufacturer has studied this intensely, and they know what the average float voltage per cell should be to maintain the perfect amount of charge and not to overcharge the battery and not to undercharge the battery. So this is from an ENESYS battery data sheet. And it says for a lead calcium, which is the most popular type of cell out there, if you had a specific gravity of 1.25 volts per cell, then you should charge anywhere between 2.21 and 2.23 volts per cell. And if you take the mean or the median of that two numbers, you will get 2.25 volts per cell. And then if it was a 1.215 specific gravity electrolyte, then you would take the mean point of 2.17 to 2.26, and that would be roughly 2.15. Yeah, because that's the 9 volts. So 2.01, something like that. Okay. But once again, 2.11. You do have to, my point is, you do have to check the battery data sheet to make sure you are charging the batteries at the correct voltage. C and D, once again, it says the float voltage should be 2.2 to 2.25 for calcium and 2.15 to 2.28 for antimony. So we're not making these numbers up. The battery manufacturer is what is driving the float voltage for the battery. It's not some made up number that you should stick by. Most people will say 2.25 volts per cell, but that's not correct. You do have to check the specifics of the battery that you're charging. And then for Hoppike, they're saying it's 2.23 volts per cell, except for this one here, which says it's 2.25 volts per cell. So you can see it's very different for each technology that's out there. Now for NiCad cells, for a 120 volt nominal system, it can be complicated because NiCad manufacturers used to always stipulate this 2-level charge system here, where you would float volt the system at 134.4, and then you would have a high level charge or a boost charge at 139.2 to up to 163.2 volts. Okay, so it was always, and they would say that you would have to do this high level charge on a regular basis, maybe quarterly or semi-annually. You would have to do this high level charge. People got fed up with doing this because it was a pain to implement in a plant setting. So what the battery manufacturers did was they actually oversized their batteries and went to a single level charge. And they're saying that for a 96 cell system, the single level charge should be 137.28 to 139.2 volts DC. So it makes it easier for the end user to keep the batteries charged at a single level. And basically they oversize the battery because they know they're going to lose a little bit of capacity because they're not following this high level charge. But it's built into the design of the battery. And the end of the discharge voltage is 96 cells times 1 volt per cell. That's an industry standard. So it's 96 volts. So the DC voltage range that your load should be able to work at is 96 volts all the way up to 139.2 for this single level system. Okay, that is for a NiCad battery. Once again, why? Well, because all of the battery manufacturers tell us how to do it. So for a single level charge for the SBH type of battery for SAFT, they're saying it should be anywhere between 1.43 to 1.5. So if you go in the middle, it's around about 1.47. Okay. And really nobody does the 2-level charge anymore. Okay. So that's where we get those numbers from. And for lithium, it gets even more complicated. For a 120 volt nominal lithium ion or a LiFePO4 system, which is usually 7-cell module with 5 modules in total, we're using the SAFT Flexion model for this. Always check other manufacturers for their specific details, okay? They're saying they have a single level charge of 140 volts DC, okay? And then they have an end of discharge voltage of 105 volts DC. So therefore, the DC voltage range that the load should be able to work at is 105 to 140 volts DC, very similar to a lead acid battery. And that's exactly what the lithium ion manufacturers are trying to do. They're trying to replicate their batteries so they can be used in an industrial setting. But Remember, do bear in mind, there are many, many different chemistries. So for an LFP, which is a lithium iron phosphate, nominal voltage is 3.2 and full charge. Here, this is actually incorrect. I pulled this table from one particular manufacturer. This can be 4 volts per cell. And that just shows how confusing data can be on the internet sometimes. But for an LTO, which is a lithium titanate oxide, they're saying that the nominal voltage is 2.4 and the maximum charge voltage is 2.8. But another lithium technology is lithium manganese, which is lithium manganese iron phosphate. The nominal voltage of that one is 3.7 volts and the full charge voltage is 4.2 volts. So you do have to be careful when specifying any of these technologies that you do follow whatever the manufacturer says you should do. And then for the salt battery or the sodium metal chloride system, there's usually 50 cells inside these modules. This is specific to the Horion or the FC Sonic UP series. Always check other manufacturers for their details. And their single level charge says it can be anywhere between 135 volts to 160 volts. Because what Horion do is they have a DC to DC converter built into their battery. So what they're saying is your battery charger can supply anywhere between 135 volts to 160 volts. It doesn't care, because what that DC to DC converter does is it changes that voltage into whatever the sodium metal chloride cells inside the battery module need. Okay. And basically what Horion is trying to do is supply a module to the stationary battery industry that you can just plug and play, because they know that most UPS and switchgear chargers are going to be round about this 135 volts DC. So what they're saying is you can just attach our battery to one of your standard industrial chargers and it shouldn't be a problem, because the DC to DC converter takes care of everything that it needs to do. Okay. The end of discharge voltage is 100 volts. So therefore, your load should be able to work anywhere between 100 volts DC. I've said here to 160 volts because the manufacturer says you can go up to that. But if you set your charger voltage to never go above 140 volts, then you can say it's going to be 100 volts to 140 volts, very similar to a lead acid battery. Trying to go over as much information as I can, and I know I'm talking a lot, and hopefully I'm not saying too much and confusing everybody. But remember, you can go back and watch the video if you have any thing that you want to go over again. Just go back to the video once it's posted and you'll be able to see it. So this is actually the specs from Horion. And remember, I said this 125 UP80 is one of the most common cell battery modules that we're seeing connected to industrial UPSs and chargers at this moment in time. So this is where we got the data from. So the nominal voltage they're saying is 125 volts. The charger range is 135 to 160. They're saying the minimum voltage it's going to go down to is 100. So that's where I got those details from. And it tells us here that the capacity is 80 ampere hours and the maximum current you can get out of this system is 120 amps. So it tells you all the stuff that you need to know for the battery on the data sheet. But what's kind of confusing about the salt battery is how they do their battery capacity. So we've got our discharge times on the left here. We've got 1 hour here down to 20 hours here, okay? And they're saying here that this column here is the termination by the BMS. And what that's saying is, that's not getting to this 105 volt end of voltage. That is the BMS actually terminating the discharge, okay? It will actually disconnect the battery after these times. So what they're saying is, if you're doing a 1 hour discharge, it's saying that you will get 61.8 ampere hours, not the 80 ampere hour that it's saying, and its end voltage will be 90 volts, and the BMS will terminate the discharge at that point. Okay. But the salt batteries work really well in this 3, 4, 5 hour range. And you can see that they're saying that you will get 80 ampere hours, okay, down to a voltage of roughly 105 volts at that range there. Okay. What I don't quite understand is they're saying that at the 20 ampere hour rate, you'll get 68.1 amps, but the BMS will terminate at 114 volts. I don't quite understand what it's saying there. It confuses me because it's saying here that the 105 volts, you will still get 68 ampere hours as well. So not quite sure. This is a newer technology, so their discharge table doesn't make a huge amount of sense to me at this moment in time. And then obviously you've got all these other end voltages as well. But what you can see here is you will get 80 ampere hours. So at the 4-hour rate, it's saying you'll get 20 amps, 4 amps. Yes, you'll get 20 amps per hour for 4 hours down to a voltage of 105 volts. And that is for the Orion salt battery. Now, for switchgear systems, this is actually a table from a type GMSG circuit breaker. This is where the load tolerances come in. So for the nominal rated control voltage of 125 volts DC, they're saying for the closing circuit and the trip circuit, you have to operate within these ranges. And for a 125 volt DC system, they're saying that their tripping and closing, their closing circuit will only operate between 100 and 140 volts DC. If you go below 100 volts, all bets are off. They're saying that their closing springs may not work, or the control circuit, and anywhere above 140 volts, you may actually burn out some of the components in the closing circuit, okay? And for the trip circuit, they're saying you can go down as low as 70 volts, okay? But once again, they're saying you may damage components if you go above the 140 volts. So that's the balance that you've got to get right. You've got to choose the right battery that the charger is going to charge between, for this system here, 100 to 140 volts without damaging the system. That's the trade-offs you have to have. And then even for our UPS systems, this is for an older AMETEK solid-state control UPS system. This is a 7.5 kVA inverter, to be exact. And what our inverter is designed to accept is 105 to 140 volts DC, okay? So the battery has to be designed to work within those parameters. So why do we use batteries? Well, hopefully you know this anyway, but the battery's only purpose is to store energy. Usually you have 480 volts coming in from your MCC, going into a rectifier charger circuit here that converts the AC into DC here. And then the DC goes onto this bus and keeps the batteries charged. And then you connect your DC loads through this DC panel. And it's only when the MCC fails, if we have a power outage, that the batteries say, okay, I'm available to do whatever you need me to do, whether it's trip, close, do whatever you need to do on the switchgear system. And for a UPS, the battery's main purpose is to store power. So once again, we have 480 volts going into a battery charger rectifier. That is connected to this DC bus. And that DC bus is keeping the batteries charged, okay? And the battery does act as a kind of buffer for any brownouts or any poor AC that's going in here. But then the inverter takes this DC and converts it back into pure AC. So the main purpose of the battery is to store power, but it does have some buffering capabilities for anomalies in the AC input supply. Okay. I didn't go, I thought I removed that. I'm not going to go into battery sizing because what I'm going to do now is quickly go into the pros and cons. of the most popular technologies we're seeing just now. So let's start with cost. So salt batteries do have a lower raw material cost potential. Sodium salt is abundant, but current battery prices are only moderate because the tech is relatively new to the industrial space. As more and more people start using salt batteries in the industrial market, we will see the prices come down and there'll start to be competition as well. Okay, lithium ion, moderate to high because it's expensive. Lithium, cobalt, it's pricey raw materials. So they are high, but they are starting to come down as well. Obviously, lead acid is by far the lowest upfront cost. It's inexpensive and mature technology. And then NiCads, a much higher initial cost than lead acid, but they have a longer service life, allegedly. Which means fewer replacements over time. You have to weigh that up, okay? And in truth, I think that's comparing it to valve-regulated lead acids. Wet cell or vented lead acid batteries tend to have the same lifespan as a NiCad battery. Energy density. Salt batteries, they have a moderate energy density. They're less compact, in other words, they are slightly bigger and heavier compared to lithium ion. Lithium ion have very high energy density, highest energy per weight amongst these four technologies, enabling lighter, smaller packs to get the same amount of energy out. Lead acids, they're the heavy guys in the industry. Very, very heavy, low energy for their size and their weight. And then nickel cadmium NiCads, they're also low to moderate, a little bit better than lead acids, but they're still big, bulky, heavy systems. Safety, salt, very, very safe. They're non-flammable chemistry with minimal fire, thermal runaway risks, very, very safe batteries, allegedly. Lithium ion, moderate, and it depends on the lithium ion technology that you choose. The LiFePO4 batteries are much safer than some of the other technologies. So everybody knows the fire risks of lithium ion. We've seen the Samsung phones going on fire. We've seen other lithium ion batteries going on fire. It is a danger, but they have tried to mitigate that as much as possible. Lead acids, very safe, stable chemistry, usually no fire, prone solvents. The main hazards are acid spills or gas if misused. In other words, if you overcharge them, it does evolve hydrogen gas, which is obviously explosive. And then nickel cadmium, very safe in operation, rugged and reliable with low fire risks, but it does contain toxic cadmium and they can overheat if overcharged as well. Environmental, salt, very low impact because it uses common materials, sodium, aluminum, and avoids scarce toxic metals, and they're easier to recycle. So A+ for salt batteries when it comes to environmental. Lithium ion is mixed. Obviously, they contain things like cobalt, nickel. Recycling does exist, but only 5% of lithium-ion batteries are fully recycled today. So, yeah, not so good when it comes to environment. Lead acid, they have hazardous lead, but because it's a very mature industry, 95% of all lead acid batteries are recycled. So it's a well-established recycling infrastructure that mitigates environmental impact. So a good rating, although they do have hazardous materials in it, the maturity of the technology means we have things in place to recycle. And nickel cadmium obviously contains highly toxic cadmium. It's very, very difficult to dispose of these, and many regions are actually phasing out of NiCad because they're just very, very hard to recycle. And then lifespan. Salt batteries have a very long lifespan. Some designs are going up to 10,000 cycles. So you are not going to run out of cycles usually in a salt battery. Very good lifespan when it comes to how many times you can use it. Lithium ion, they have quite high cycles as well, between approximately 1,000 to 2,000. Some cells are getting up to 3,000 to 6,000, especially the LiFePO cells. So that's pretty good. Lead acids, not so good. Typically a few hundred cycles before performance drops and requires maintenance. Okay, so lead acids cycles aren't great compared to other technologies. And NiCads, once again, very good when it comes to cycles. But there is the minimal memory effect that you have to take into consideration as well. Okay. And then scalability. Salt has a high potential. They're built from abundant resources, but obviously it's a newer technology and it has to be adopted before it can be scaled up. So China is leading the way on this. They're using salt batteries quite a lot, and it's just starting to trickle down into our markets now as well. So scalability is going to be good. Eventually. Lithium ion is a mature industry, so they're built in massive scale. The only thing that they have problems with is the scarcity of the lithium cobalt supplies. Okay, lead acid, mature, widespread, not a problem. It readily available and very scalable. And then nickel cadmium, because there's limited growth, NiCads, it's declining due to their environmental regulations. So it's really niche markets that are using these now. NiCads are tending to not be used as much as they used to. Okay. And the last thing I wanted to talk about was BMS, which is a battery maintenance system or battery monitoring system, and the internal charger. So for a salt battery, the most common North American model, which is the Horion model, does have a BMS system inside it that monitors the cells, and it also has an internal DC to DC converter. Okay? So there is electronics inside the battery. To me, that is a concern. We have to see how that works out over time, but especially the fact that these operate at 300 degrees Celsius and the electronics is within that module. Now, it might not be at 300 degrees, but there is going to be heat getting out of that battery. The electronics are going to be warmer than they should be. So I believe that they may, in truth, fail earlier than expected. It has yet to be seen. Okay. Lithium ion also has BMS monitors inside them, and they monitor the cell voltage and temperature and also perform cell balancing. Okay, so there is once again electronics inside of a lithium ion battery. It's not just a battery like a lead acid battery that you just connect and forget about and do your regular maintenance on. Lithium ions have an active BMS system that is constantly trying to keep all the cells very close in voltage to one another. So there is electronic balancing that's going on inside that battery. Once again, that is a concern to me. Whenever you have electronics in a battery, I don't think the battery technology is going to fail. I personally think the electronics is going to fail. But remember, this is my opinion. It's not saying that it's going to happen. It's just with all my experience working in electronics, power electronics for the last quarter century, that is always going to be a failure point in my mind. Lead acids, you don't need a BMS system, but you can buy one if you want to and connect it to your system to aid in your maintenance. And NiCads, once again, none required, and it can be purchased. So if you asked me what my opinion is of all these technologies, I would say salt, the jury is out. It hasn't been used enough for us to know. I'll give you some history. When the valve-regulated battery came out, it was sold initially as a maintenance-free battery. You didn't have to do anything to it. You would just connect it to your charger and it would just work. Within 5 to 8 years, we were seeing a huge amount of valve-regulated batteries fail. So, you started having to do maintenance on them. IEEE started coming up with plans on how to do the maintenance. You can't see the electrolyte inside that battery, so you had to use tools to figure out what the internal resistance was. So, salt batteries are being sold as maintenance free, and you just plug them in and forget about it for 20 years and they'll do their job. Yeah, that could be true. I just don't know. And it's this DC to DC converter that worries me in these salt batteries. It is an electrical component that is going to get warm. And I just see that being problems. I really, truly, unless they figured something out, I just don't see how that is not going to be a problem. Lithium ion, in truth, I think it's good technology. I think they've now got to a point where we're seeing less and less systems go on fire, which is obviously a huge concern to any plant out there who's deciding to choose lithium ion batteries. So I see lithium ion as a good alternative. But you still do have to keep that safety at the back of your mind that if it did go out of control, that fire is nearly impossible to put out. It's a concern. Lead acids, they're just good batteries. Okay, yes, they're big, they're bulky, they're clunky, but they're tried and tested, especially the vented cells where you can see the electrolyte. They're just the industry workhorses. Yes, you have to perform a lot of maintenance on it, and that maintenance can be costly because IEEE has told you what maintenance that you need to do to make sure that the batteries don't fail. And I get it. It's very time consuming. It's very monotonous. And it's a pain, but they work, and they've worked for a very long time. And NiCads, I do like NiCads. NiCads are good batteries, but they just haven't been adopted. The recycling is terrible, and they just didn't find a way into the stationary industry as much as they maybe could have. Great technology, and they work really, really well. But yeah, you just don't see as much of these in North America as you do in Europe. So, I'm not going to recommend any of these. Obviously, you can probably tell I prefer lead acid because that's just what I'm used to and it's what I know works. I think salt batteries, they could be great, but the jury is out. And I think lithium ion is a good choice, as long as you have everything in place to mitigate any fires. That's my opinion. And look at that. As always, I have spoken way too much and we are 7 minutes over. So I do apologize to everybody. Hopefully that was interesting. Let's go to the Q&A and see what questions we have. Okay. Are there any visuals being displayed? Yes, there are. I don't know why you couldn't see that, Ty. Are different chemistry batteries all 2 volts? No, they're not. Hopefully, Brian, I explained that as time went on. Let's have a look. Getting used to this chat bar. What applications industries are they using salt batteries for? Very good question, Bryce. We're seeing them more and more in the industrial. So we're talking about petrochemical refineries and plastic plants, and we're starting to see it in switchgear as well. Basically, anywhere people are taking this maintenance-free sales pitch that they're doing and saying, wow, I can save so much money if I go to salt batteries because I'm saving on maintenance over 20 years, which is a huge amount. And I get that. But I think you have to be very careful with these salt batteries until they have proved themselves over 20 years. So they are going everywhere, Bryce, and we're seeing a lot of demand for salt batteries at present. Okay. Tom, please comment on saltwater batteries. What is the current state of technology, and is anyone working on commercial production? Actually, Tom, to be honest, I'm not a battery expert. I know a lot about batteries, but it's more about what we see in the industrial world. I know there are some salt batteries that they don't have to be heated up to 300 degrees, and they're starting to talk about using salt batteries in EV vehicles, electric vehicles. So, and they don't have to be heated up to 300 degrees. So there is a lot of R&D research being done on salt batteries, and I'm guessing that's when you say the saltwater batteries as well. So I can't comment on it as much as I would like. Maybe I'll do some research, and in maybe 6 months I'll do another battery presentation that mentions salt batteries, saltwater batteries in particular. Has anyone started using sodium-based salt batteries in the industrial UPS and substation world? Pratik, I hope I've answered that question. Yes, it is definitely being adopted. We have seen at least a dozen, if not more, in the first quarter of 2026. People contacting us to say, do we have to change the charging specifics of our UPSs or charger systems because they're installing sodium-based batteries? So yes, it is definitely being adopted in the industrial UPS and substation world. Glenn, compared to VRLA, how are salt and LiFePO batteries affected by charger ripple? Okay, and the lifespan affected more, the same, or less? Okay, Glenn, that's a very good question. And I'm kind of annoyed at the salt batteries because the salt battery manufacturers are saying that you have to limit the ripple going into their salt batteries. Now, remember, there is a DC to DC converter between the charger and the batteries themselves. Okay? So any ripple that the charger is creating does not get to the battery. Okay, the DC to DC converter should take care of that. And if you know anything about DC to DC converters, we use them in our UPS systems as power supplies. And basically, you buy a power supply that can do anywhere between 100 and 240 volts AC, and it converts that to DC. And that same power supply, you can put anywhere between 100 and 140 volts DC into it, and it will give you whatever DC voltage you want out of it. So the technology of a DC to DC power supply should not be affected by ripple. So it is really confusing me why the salt batteries are saying that ripple affects their batteries. And they have not given us any good answers as to why that is at this moment in time. So I can't answer that, but from what I know about batteries and DC to DC converters, Glenn, you should have no issues whatsoever by connecting a high ripple charger into a DC to DC converter. But once again, that's my opinion. If Horion came back and gave me documented reasons for why they're saying that, then I may change my tune. But at this moment in time, there is nothing that tells me that ripple is going to affect a salt battery. For LiFePO batteries, for lithium-ion batteries, I don't think they're really, I can't remember there being high tolerances on lithium-ion batteries when it comes to ripple. But don't quote me on that because it's been a while since I looked at the data sheet. What I might do, Glenn, is look a bit more in depth and get back to you on that one because I'm not 100% sure how ripple affects LiFePO, but I think it is less than VRLA. And in truth, I'll tell you a secret, Glenn. I think it was, I can't remember who did the research. It was either Eaton or somebody big like that. They did research on VRLA batteries because obviously all of the VRLA battery manufacturers say that you need to keep the ripple down to a minimum, and they stipulate what that minimum ripple should be. Well, one of the big manufacturers of UPSs and chargers did a study, and they put a high amount of ripple into VRLA batteries, and they did not see a huge impact on internal temperature, which is what kills VRLA batteries, and because it causes the electrolyte eventually to dry out the temperature. So they didn't see a huge increase in temperature or lifespan of that battery. And if you search the internet, you will, I can't remember what it's called, but if you type in white paper on Ripple for VRLA batteries, you'll find this white paper, and it's quite interesting because it always confuses me why the battery manufacturers stipulate such a low amount of ripple, yet there's really no great evidence to show that ripple does affect batteries in the wild. There's no good study that says that, as far as I'm concerned. Okay, maybe somebody can send me that and I can read it and I'll change my mind on that. But at present, there is a white paper out there. A study was done and it said that ripple didn't even affect VRLAs as much as they say. And the pros and cons of a lead acid 2-volt jar versus a 12-volt jar system when both systems are configured for the same voltage and capacity. The industry standard answer to that is to use a 2-volt system because the life of a 12-volt system is typically less than a 2-volt system. I've never been given a really good answer to why. And it's probably because when you have 6 jars, especially in a VRLA battery, in one enclosed block, then heat, I suppose, compounds in some ways and can cause that block to be hotter than a single cell would be, because a single cell is always going to have an air gap on both sides, so they don't get as hot. So I would assume that is what causes 2-volt jars to be better than 12-volt jars. But in most cases, it's down to preference, size, and what you can fit into the space that you have available. Gigan has asked, what are my thoughts on electrostatic storage, supercapacitors or ultracapacitors? I have to say, I have looked into this a little bit, but there is nothing at this moment in time that does what we need it to do and gets us minutes or hours worth of backup time. I may be wrong. The technology may be moving. I do try and keep my finger on the pulse, but I have not seen any supercapacitor or ultracapacitor that gives us the amount of backup time that we're looking for in the industrial industry. Juan says VRLA don't require spill containment pan. No, absolutely not. It's a VRLA battery. It does not require a spill containment pan. Now, you do have to go with your electrical code for wherever you live, but or wherever it's installed, should I say. But a VRLA battery has, if it's a gel cell or if it's a glass mat cell, there is no free electrolyte. So if there is a crack in the jar, it's not going to leak a huge amount of electrolyte to the floor. So you do not need a spill containment pan for a VRLA system. Which battery type is better to withstand temperature variations? Pratik, very good question. And that is where salt batteries really come into their own. You can put a salt battery outside in 110 degrees Fahrenheit weather, and it doesn't care, because actually it helps because they need to be at 300 degrees C. So that's one of the selling points of a salt battery, is very, very tolerant to temperature. It's not really affected at all. Once again, that's what the manufacturer is saying. That's what most reports we are seeing say. I still think the jury is out. We need at least another 5-10 years of seeing these salt batteries in operation before we make a good decision on whether they are right for the stationary battery industry. But They are being sold as very, very temperature tolerant and by far the best for the four technologies that we've mentioned today. Wow, 20 minutes over budget. I am so sorry, guys, to keep you running as long as I have today, but batteries always seem to be a very popular topic. So I appreciate all the questions. I love it when we get questions. It really means that what I'm talking about is interesting and leading you to have questions on what we discussed. So what I'll do is I'll leave the Q&A open just for a little bit longer. And what I'll do is I will say thank you very much for taking time today to listen to me. Our presentation will be provided, will not be provided. We never give our PDFs out, but you can get the replay of the YouTube video on our YouTube site. London has been kind to put that in our chat bar. The link is there. If you go link, bookmark, and then by tomorrow, the video will be uploaded and you can go and watch it again, share it, and do whatever you want.